afternoon, everyone. Today, now it's my turn to give you a brief introduction about my research background and the work that I'm currently working on. So let me start my research background from a broader aspect, which is Earth system science. All processes of geomorphology fall under the rubric of Earth system science, and we must master parts of many disciplines. So for Aeolian geomorphology, those would include climatology, fluid dynamics, engineering, and ecology. Aeolian process is a main driving force for Earth's landscape change, especially for those arid, semi-arid, and coastal environments. For example, the bury of railway by drifting sand, or the house climbs from dune migration, or like the land degradation issues here, or sometimes with human health issues from dust devils. And also the blowing sand contribute to the formation of coastal dunes, which support important ecosystem and protect onshore development from coastal erosion or storm surge. So in the next few slides, I will give you a brief introduction on two of the projects that I had worked on. The first one is associated with green flows on the leeward side of sand dunes. As you see here, we use terrestrial radar scanner and video camera to record what's happening on the leeward side of sand dunes. And this is a brief result, what we got. And the left two panels are the green flow shapes that we extracted from terrestrial radar scanner. We also calculate the associated amount of sediment transport, the velocity of the green flows, etc. And all those work has been published. If you are interested, you can find the paper online. And then the second project I want to present is about granular electrification during Aeolian sand transport. It's still going on. The goal of this project is to figure out the effect of granular electrification during a sandstorm or dust storm. We want to see how the effect will cause more sediment transport or less sediment transport. Also, we quantify the charges of the particles during a sandstorm. And here's a video that shows our fieldwork last year in Mojave Desert, California. So actually, this day was a pretty dusty day. I mean, the highway is even closed because many sand has been blown on the road. Okay, from this slide, I will start to talking about the work that I'm currently working on here, mainly about Aeolian EROsion model development. I won't get you bored by presenting so many complicated mathematical equations because that's the main part of the model. But anyway, I will give you a brief introduction about this model from three aspects: model input, model development, and outputs. In the next few slides, I will fill in more details about these three aspects. So the goal of our project is the development of AERO model as a wind erosion and air quality decision support tool that contributes to management objectives of partner agencies. So for the model input part, we use the micrometeorological data, mainly the wind speed data. The model used the cup anemometer data previously, but right now we have more advanced instruments, which are 3D sonic anemometers, can be better used to quantify the surface shear stress, regardless of the stability of atmosphere or the estimations on surface roughness length. And the second part of the inputs information is the soil information. Previously, our model mainly include the grain size distribution patterns. We are trying to working on including more factors like soil moisture or organic matter. For the vegetation cover, the input value are the measurement from standard National Wind Erosion Research Network methods. Right now, I'm thinking about maybe we can include more collaboration work with a team of rangeland hydrology and erosion model to see the combined effects of fluvial and wind erosion processes. So for the model development, my contribution to this project will be on the modification of drug partition scheme. So technically want to resolve the effects of turbulent flow around the plants and other erodible and non-erodible roughness. Previously, our model mainly includes the shelter effect immediately behind the plants, as you see by those black arrows indicate the magnitude of wind speed. Right now, we are trying to figure out what's happening around plants, in 2 dimensions instead of 1 dimension. Therefore, we set urban sensors by those orange dots around the plants to measure surface shear velocity or shear stress. Also, those are the sonic anemometers around the plants. And by the way, this graph is a top view, and here is a graph shows the side view of the fluid field around the plants. Those arrows indicate the velocity, and those circles, square circles, indicate the turbulent structures. So for the model output measurement, we will include the vertical dust emission scheme in the model calibration. This is the part that our model hasn't included because the data limitations on the dust measurement collection. So that's the part we will work on. So here I will start talking about part of the results that I got since I started the work here. Right now I'm focusing on the different approaches to derive surface shear stress from sonic anemometers. Later I will show you some results. My next step is to compare the shear stress measurement to the urban sensors on the barrier surface. So it's still on the calibration stage. And here is a result example. So in general, there's no I use 4 methods to derive surface shear stress from sonic anemometers. In general, there's no significant difference among different methods. As you see, the p-value here is less than 0.05. Maybe some of you are already familiar with the last 3 methods: double rotation, triple rotation, and planar fit. Method 1, it is the most recently published method. It needs the minimum amount of analysis steps and rotations, and also it gives us pretty reliable results. Since method 1 is relatively new, there are not a lot of data analysis to test this method. In this slide, there are 2 graphs. I show you a direct comparison between the newest method on the vertical axis and the most traditional method, which is double rotation, to show the direct comparison between the most recently published method. So in general, it gave us a pretty good reliable estimates on shear velocity. And the left graph shows all the data at all thermal conditions, either atmosphere is stable, unstable, or neutral. And the right graph is after we do quality control on momentum flux. So we choose the first best levels of quality data. The fading line becomes much better, as you can see on the graph. So lastly, I want to talk about our field plan in the coming spring. Brandon and I plan to do a field experiment on dust levels at Lordsburg Playa. We will use the accelerometers to detect the height profile of dust levels. As you see, this is the instrument, how it looks like. We already have this experiment, this instrument at hand. So it's, we plan to do a field experiment in the coming spring. Okay, that's pretty much I want to say about my research background and the work I'm currently working on. Any questions are welcome.